In considering the fate of a universe where all stars have gone out, the first step is to understand the fundamental role that stars play in the cosmic environment we inhabit. Stars are essentially massive nuclear reactors, fusing lighter elements such as hydrogen into heavier elements while emitting vast amounts of light and heat. This energy output not only illuminates the universe, but also sustains planetary environments where life as we know it can flourish. Without stars, the universe would plunge into total darkness, accompanied by a severe drop in temperature. Exploring how humanity might survive in such a scenario requires delving into both astrophysics and potential energy sources beyond stellar radiation. When all stars extinguish, either because their fuel is depleted or due to more exotic cosmic phenomena far beyond human timescales, the universe would transform dramatically. The nights we experience now, dark as they may sometimes seem, are in fact brightened considerably by starlight, including the glow from our closest star, the Sun. This sunlight and starlight provide the warmth necessary to maintain conditions for life. Without this essential energy input, temperatures throughout the cosmos would fall drastically, eventually approaching absolute zero, the coldest temperature possible where atomic motion nearly stops. It is important to understand that current astrophysical models predict stars will not go out abruptly. Instead, over trillions of years, stars will burn through their fuel, passing through various evolutionary stages. Many will expand into red giants before shedding outer layers, then contract into white dwarfs, neutron stars, or black holes. Eventually, all stars will exhaust their nuclear fuel and no new stars will form, because the necessary gas clouds for star formation will have been consumed or dispersed. The universe will enter a stage often referred to as the degenerate era, where white dwarfs, neutron stars, and black holes dominate, and no fresh light is produced. In such a cold, dark universe, how could humanity, or any form of life, continue to survive? The first challenge is energy. Life, as we understand it, depends on a continual input of energy to organize matter and sustain biological processes. On Earth, this energy primarily comes from sunlight driving photosynthesis in plants, which forms the foundation of most ecosystems. In the absence of starlight, alternative energy sources must be sought. On Earth today, even life forms in extreme darkness survive by tapping non-solar energy sources. Deep-sea hydrothermal vents, for instance, support ecosystems independent of sunlight. These vents emit heat and chemicals from the planet's interior, which certain microorganisms use to fuel life through chemosynthesis rather than photosynthesis. This demonstrates that life can persist relying on gravitational energy stored within a planet rather than sunlight. In a starless universe, human survival might depend heavily on similar principles. Harnessing gravitational energy, nuclear reactions, or geothermal heat from planetary bodies. Earth, for example, itself generates heat through radioactive decay deep within its core. This internal heat energy maintains the planet's molten outer core and fuels volcanic activity. Over extremely long periods, even as the Earth cools slowly, this geothermal energy could carry on providing a heat and energy source for a time. Moreover, advanced technology could allow future humans to tap directly into nuclear energy, which is fundamentally the conversion of mass into energy according to Einstein's famous equation, E equals mc2. Nuclear reactors convert tiny amounts of uranium or thorium into energy with high efficiency and no reliance on solar input. This could be a cornerstone of a post-stellar civilization's energy infrastructure. Another intriguing possibility would be utilizing the energy stored in black holes. Black holes, contrary to common misconception, can emit energy through a process known as Hawking radiation. This radiation is extremely faint in typical black holes, but over unimaginably long timescales, it allows black holes to lose mass and evaporate. Advanced civilizations might one day develop methods to harness this radiation or tap into other forms of energy surrounding these exotic objects, including energy from accretion disks or jets emitted while consuming matter. But energy isn't the only concern in a universe without stars. Light itself plays a crucial role in biology and technology. In perpetual darkness, what would be the role of artificial illumination? On Earth, light is fundamental not only for vision, but also for regulating biological rhythms. Our circadian clocks depend on the regular cycle of day and night governed by sunlight. In the absence of natural light cycles, humans would need to establish artificial lighting systems that simulate these cycles to maintain health and psychological well-being. Light-emitting diodes, LEDs, and other high-efficiency artificial lighting technologies could serve this purpose. These devices convert electrical energy into visible light with minimal heat loss, allowing constant illumination as needed. On a larger scale, such technologies might be integrated into habitats designed to support life in total darkness, perhaps built underground or within shielded environments to protect against cold and radiation. Temperature regulation would also be paramount. Without any stars to warm planets, maintaining habitable temperatures would be challenging. Earth's atmosphere and magnetic field currently protect life from harmful cosmic radiation and help regulate temperature, but they rely indirectly on solar energy. In a starless universe, artificial habitats might need enormous insulation systems, thermal energy recycling, and effective waste heat management to create livable environments. Human survival might ultimately hinge on constructing massive, enclosed biospheres, self-sustaining habitats designed to operate independently from external energy and light sources. These habitats could recycle air, water, nutrients, and waste with high efficiency, employing closed-loop ecological systems engineered to support life indefinitely. Research in efforts like the Biosphere 2 project on Earth provides a proof of principle for such complex ecological systems, though scaling them to a civilization-wide level in a cold, dark universe would be an exceptional engineering challenge. Beyond individual planets, humanity's survival could also depend upon migration to regions in space where residual energy exists. Rogue planets, for example, are planets that have been ejected from their star systems and drift through interstellar space. While they receive no stellar heat, some of these planets might retain internal heat from radioactive decay and tidal forces, offering pockets of warmth. If equipped with energy harvesting technologies and enclosed habitats, humans might find refuge on such worlds. Additionally, it is notable that cosmic background radiation, a faint glow from the Big Bang itself, still permeates space. Although this radiation has been cooling and thinning as the universe expands, it might provide an almost unimaginably faint energy source thousands of billions of years in the future. However, the energy density of this background radiation is extremely low, indicating it would be insufficient to sustain biological processes without amplification or concentration technologies. Life's chemistry also relies on temperature and the availability of water and various elements. In the freezing darkness, traditional forms of liquid water on planetary surfaces would be scarce, since water freezes at 0 degrees C under Earth's atmospheric pressure. Some may exist in subsurface oceans, warmed by geothermal energy. For example, icy moons such as Europa and Enceladus in our solar system already show evidence of such oceans beneath thick ice crusts. If humanity were able to colonize similar environments elsewhere, these subsurface reservoirs could offer a stable habitat, shielded from the cold and providing water necessary for life. Considering human biological needs, the absence of vitamin D synthesis from sunlight is an important factor. Humans produce vitamin D when ultraviolet light from the sun interacts with skin. In eternal darkness, supplementation or artificial production of essential vitamins and nutrients would be necessary to maintain health. This highlights how tightly human biology is linked to stellar energy and suggests that living in a starless universe would require technological compensations in medicine, nutrition, and lifestyle. Although the prospect of a universe without stars appears bleak and inhospitable based on current understanding, It's important to recognize that living systems, especially intelligent ones, are remarkable in their ability to adapt to extreme conditions. Earthly life has thrived in deep caves, beneath ice sheets, and near scorching hydrothermal vents, showing that life can flourish without sunlight under the right conditions. To survive in eternal darkness on a cosmic scale, however, humanity would need to combine biological adaptation with advanced technology. From harnessing nuclear and geothermal energies, to developing artificial biospheres with controlled lighting and temperature, to possibly exploiting the energy around black holes, every strategy would emphasize sustainability and efficiency. Technologies employed would need to operate on unprecedented timescales, with maintenance and resource recycling systems designed to function independently for millennia or longer. In summary, a universe in which all stars have gone out would pose extraordinary challenges to human survival. The loss of stellar light means losing warmth, natural illumination, and a crucial energy source. Yet, by understanding alternative energy sources like geothermal heat, nuclear fission, and possibly black hole radiation, combined with advanced habitat technologies that simulate light and maintain optimal living conditions, humanity could, in principle, endure even in eternal darkness. The vast age and scale of the universe provide an ample time frame for such adaptations, since this stellar extinction is a process projected to occur over trillions upon trillions of years. Exploring this scenario not only prepares us to imagine life in extreme environments, but also deepens our appreciation for the sun's critical role in sustaining life on Earth today, and could inspire future innovations in sustainable living, energy efficiency, and planetary engineering in times both near and distant. Beyond the immediate challenges of energy, light, and temperature regulation in a starless universe, an often overlooked factor is the profound impact on cosmic chemistry and the cycles that underpin the formation of new matter and complex structures. Stars are not just beacons of light and warmth. They are the forges in which most of the elements heavier than hydrogen and helium are created. This process is vital in shaping the material conditions for planets, life, and the broader ecosystem of the cosmos. To understand this, it helps to explore stellar nucleosynthesis, the process occurring within stars where lighter atomic nuclei fuse together to form heavier ones. In the cores of stars like the Sun, hydrogen nuclei fuse to produce helium, releasing enormous energy. In larger, more massive stars, this fusion chain progresses to create elements such as carbon, oxygen, silicon, and iron. These elements are later expelled into space through stellar winds or dramatic events like supernovae, enriching the interstellar medium, the diffuse gas and dust between stars, with the building blocks necessary for new stars, planets, and potentially life. When stars cease to shine, this cycle grinds to a halt. No fresh elements are produced and dispersed, and the universe's chemical evolution effectively freezes. Over time, this leads to a matter composition dominated by the remnants of stars already formed, white dwarfs, neutron stars, and black holes, along with a gradually depleting amount of gaseous material. Since new stars require clouds of gas rich in these heavier elements to form planetary systems, the universe's capacity to regenerate complex structures diminishes. This chemical stasis means that, for any future generations attempting to sustain life or rebuild civilizations, the raw materials needed for everything from organic molecules to complex minerals would become increasingly scarce. The implications for technology are significant since many useful materials derived from elements like iron, copper, and rare earth metals originate through stellar processes. Without the continuing cycle of star birth and death, the universe's resource diversity would contract severely. In turn, this limitation on chemical recycling drives home the importance of sustainability and efficiency in any civilization that persists beyond the stellar era. Technologies assuming infinite access to certain elements would fail unless designed around closed-loop systems, where every atom is reused and recycled across millennia. For example, even seemingly abundant elements must be conserved carefully, and the challenge of mining or refining resources without stellar heat or light compounds the difficulty. Moving from material scarcity to physical conditions, gravity would remain a key force shaping the future of matter in a universe without shining stars. Objects such as white dwarfs and neutron stars are incredibly dense remnants stabilized primarily by quantum mechanical forces opposing gravitational collapse. Black holes, on the other hand, represent regions where gravity dominates completely, compressing matter beyond typical atomic scales. These dense objects persist far longer than stars powered by nuclear fusion and dominate the cosmic landscape during the so-called degenerate era. Interestingly, though these compact objects lack ongoing nuclear fusion and the light associated with it, their gravitational fields still influence their surroundings. For instance, remnants bound within galaxy clusters continue to interact gravitationally, occasionally generating energy through collisions or the accretion of sparse gas. Even in the dim universe, gravitational interactions might sporadically produce low levels of radiation or kinetic energy, providing subtle energy fluxes on which specialized life or machines might capitalize. Another feature that grows increasingly important in such an environment is entropy, the measure of disorder or energy dispersal in a system. Without stars injecting new energy into the environment, the universe trends inexorably toward maximum entropy, a diffuse and uniform cosmic condition often described as the heat death scenario. In this state, energy differences needed to do work vanish, and the universe reaches thermal equilibrium at near absolute zero temperature. While some might view this as the ultimate cosmic endpoint, the path to it is long and stages exist where pockets of complexity or local order can persist. For instance, matter can remain gravitationally bound in dense structures, and energy gradients could still support processes akin to life or mechanical activity in those niches, provided an energy source is harnessed. The difference is that, on cosmic scales, these islands of complexity grow ever more isolated and rare. One remarkable consequence of continued universal expansion is that many galaxies will move beyond each other's event horizons, effectively slipping out of causal contact. This isolation affects not just the exchange of light and matter, but the potential for communication, migration, or resource sharing between civilizations. In a starless future, any surviving intelligent species might find themselves stranded in shrinking habitats without external support, their options confined to local resources and energy. Given this inevitability, it's worth examining the prospects for engineering solutions that do not depend on stellar inputs or abundant external resources. Some theoretical concepts suggest that, by manipulating matter and energy with extraordinary precision, advanced civilizations might tap into the fundamental vacuum energy of space itself, a form of energy hypothesized in quantum field theory to pervade the vacuum. Although practically harnessing vacuum energy remains beyond current understanding, it represents an intriguing possible energy source once stars fade. Similarly, the extraction of energy through matter-antimatter annihilation is another high-efficiency method available in principle. While antimatter is scarce naturally, artificial production might be possible given sufficient energy and technology, allowing future societies to store and deploy intense energy in compact form. Such technologies could compensate for the absence of steady natural stellar radiation and provide an energy basis for space travel or planetary maintenance. Furthermore, as traditional life forms dependent on photosynthesis and solar cycles would struggle, alternative biochemistries might be considered. It's speculative at present, but some research into extremophiles, organisms thriving in conditions hostile to most life, reveals metabolism based on chemical gradients or radiation sources unrelated to sunlight. Microbial life in superheated or radioactive environments shows that life can, under certain conditions, exploit energy sources tied to geothermal or radioactive decay rather than photons. Building on this biological flexibility, Closed ecological systems for humans and complex multicellular organisms would need to mimic or substitute for key natural processes such as photosynthesis. Artificial photosynthesis, technologies that replicate the chemical steps plants use to convert light, water, and carbon dioxide into energy-rich compounds, could perhaps be adapted to function using artificial light or other energy sources. Such systems would be central to long-term food production in starless habitats. On a technological front, energy storage becomes a critical challenge when external energy inputs are sporadic or minimal. Batteries, capacitors, and other storage media must not only hold vast amounts of energy, but preserve it over very long periods. Emerging materials such as solid-state batteries and novel superconductors may enable future civilizations to store energy more efficiently and with less degradation, supporting consistent power distributions for habitats and life support. Transport and communication in a dark, starless universe would also transform significantly. Navigational references based on starlight, the basis of celestial navigation used by humans for millennia, would disappear, necessitating entirely new methods for orientation. Technologies relying on radio waves or other electromagnetic signals might persist, but face limitations due to increased distances and energy requirements. In such conditions, navigation might rely more heavily on onboard inertial systems, gravitational mapping, or quantum-based sensors capable of detecting subtle fields and particle interactions. Additionally, the use of neutrinos and gravitational waves, which can travel vast distances unattenuated by dust or gas, might become essential for long-range communication and sensing. Leveraging these signals would require advanced detectors and deep understanding of fundamental physics. Another important consideration is the psychological and societal impact of living in an eternal dark environment. Human beings evolved under day-night cycles governed by the sun, and these natural rhythms regulate sleep, mood, and even cognitive function. In a universe without stars, artificial lighting regimes and environmental designs must address the mental health challenges arising from disconnection with natural light cues. Long-term space habitats or underground colonies would need to incorporate architectural and social designs that simulate natural environments, including adequate lighting spectra and intensity variations to signal day and night or other cycles. This could help mitigate effects such as seasonal affective disorder, SAD, and maintain circadian rhythms essential for health and performance. Cultural adaptation would likely go beyond biology and technology. The loss of celestial reference points, the stars, constellations, and night sky, would change human culture, history, and storytelling. Since the stars have been integral to navigation, calendar systems, mythology, and art for thousands of years, their absence might foster new ways of relating to the cosmos based on the experience of darkness and the exploration of alternative cosmic phenomena. In summary, the extinguishing of all stars challenges humanity and any other potential life forms by removing energy sources, altering material cycles, and transforming environmental conditions. The responses to such changes must be multifaceted, integrating physics, chemistry, biology, psychology, and engineering in unprecedented ways. While the cosmos in this state appears overwhelmingly hostile, the resilience and ingenuity that life on Earth has demonstrated give reasons to consider that survival, though hard, may not be entirely impossible. Looking further ahead, as we contemplate these drastic changes, it's useful to reflect on the current position of our Sun and the expected timeline of stellar evolution. The Sun, a middle-aged star, is about 4.6 billion years old and expected to continue fusing hydrogen for roughly another 5 billion years. This provides a substantial but finite window of opportunity for life on Earth as it exists today. Eventually, the Sun will exhaust its hydrogen fuel and transition through phases that culminate in a white dwarf remnant. This familiar timeline emphasizes that the sudden disappearance of stars is not a near-term possibility, but a slow, gradual process unfolding over cosmic epochs. This slow pace allows ample time for civilizations to develop technological solutions and adapt to changing cosmic conditions. It also means we have, at present, nearly unfathomably long periods of stellar energy still fueling life's advancement and discovery. Developing precise models of these future epochs depends on astrophysics, nuclear physics, and cosmology. These models help scientists understand when and how star formation will cease, how black holes evolve and evaporate, and what the long-term fate of matter and energy in the universe might be. Such theoretical knowledge underpins the practical insights we derive about survival strategies without stars. As a final note for this segment, the scientific exploration of a starless universe also illuminates fundamental questions about the nature of life, energy, and complexity. It forces us to strip away assumptions about the indispensability of sunlight and visible light, pushing us to think about how life and civilization might exist under radically different conditions. This kind of thinking enriches the search for extraterrestrial life by broadening the range of environments considered potentially habitable. Moreover, this exploration underscores the intricate interdependence of cosmic phenomena, the interweaving of nuclear physics inside stars, planetary environments, biological systems, and intelligence. Stars are more than just astronomical objects. They are central pillars on which much of the known universe's structure and meaning are built. In upcoming discussions, it will be valuable to delve deeper into the fate of stellar remnants, the role of black holes as energy sources, and the possibilities and limitations of artificial energy and life support systems in the relentlessly dark cosmos. Further consideration of the philosophical and practical implications of all stars out scenarios will enhance our understanding of humanity's place in the unfolding universe. Focusing now on what remains once stars have flickered out, the cosmic landscape in a universe without shining stars is dominated by stellar remnants that, in many ways, define the new cosmic order. White dwarfs, neutron stars, and black holes, all formed in the final stages of stellar evolution, become the primary matter configurations shaping the structure and potential energy flows in this dim future. White dwarfs are the result of stars like the Sun that have exhausted their nuclear fuel and shed their outer layers, leaving behind dense, Earth-sized cores primarily composed of carbon and oxygen. These remnants no longer undergo fusion, but glow faintly from residual thermal energy, slowly cooling over billions of years until they become black dwarfs, cold, dark stellar corpses. Although white dwarfs no longer provide significant illumination or heat, their gravitational influence continues to hold together any surrounding matter, and by extension, maintain the integrity of planetary systems that survived their parent star's death. Neutron stars arise from more massive stars that explode as supernovae, leaving behind incredibly dense objects composed mostly of neutrons. About 20 kilometers across, but with masses greater than the Sun's, neutron stars have extraordinarily strong gravitational and magnetic fields. Some spin rapidly, emitting beams of radiation that sweep across space as pulsars. While their emissions are far weaker than active stars, in a starless universe, these sources would stand out as rare and localized pockets of electromagnetic energy. Black holes, meanwhile, form when the mass of a dying star collapses beyond the neutron star stage, squeezing matter into a singularity with gravity so intense that not even light can escape. Contrary to their ominous reputation, black holes are not just cosmic sinks, but dynamic entities that play vital roles in galaxy formation and evolution. In a starless universe, black holes become the ultimate long-lived objects, persisting for timescales far exceeding the lifespans of stars. They offer a potential, albeit limited, energy source through mechanisms like Hawking radiation, particle emissions caused by quantum effects near the event horizon. Although extraordinarily faint, Hawking radiation theoretically allows black holes to slowly lose mass and evaporate over incredibly long timescales, releasing energy in the process. This process, taking longer than the current age of the universe to emit significant energy from stellar mass black holes, could be one of the few natural sources of radiant energy in the deep future. Thought experiments in physics even imagine advanced civilizations near black holes designing methods to harness such energy, capturing radiation, or exploiting the dynamics of matter falling into these objects. Meanwhile, the universe itself continues expanding, driven by dark energy, a mysterious force causing accelerated expansion. As galaxies drift farther apart, their relative velocities increase, and many galaxies become unreachable, effectively isolated by horizons beyond which signals cannot travel. This cosmic acceleration isolates star remnants and any habitable zones, making intergalactic travel or communication increasingly impractical over time. The baseline energy environment thins as matter disperses and cooler temperatures dominate. Within this evolving context, a critical question for any surviving life or intelligence concerns the availability and management of water and other volatiles essential for biochemical processes. In a starless universe, surface water on planets and moons would freeze solid due to plummeting temperatures. Where liquid water persists, it would likely be trapped underground or beneath thick ice layers, warmed by still-active geothermal processes. Such subsurface oceans exist today in some icy moons of our solar system, like Europa and Enceladus, and represent potential habitats shielded from the extreme cold and radiation outside. These subterranean habitats offer a conceivable refuge where life could persist independent of solar heat. If humanity or its descendants were to colonize such environments, they would need technology to access, maintain, and manage these liquid reservoirs, extracting energy efficiently from geothermal heat and recycling nutrients within closed ecosystems. The challenges are daunting, but build on the natural precedents already observed in Earth's extremophiles and deep biosphere. From a technological perspective, energy storage and resource recycling become paramount in such environments. Without stars to replenish energy naturally, every watt must be conserved, and recycling extended to all materials. Advanced material science might produce super-durable synthetic compounds able to withstand geological pressures and long timeframes while supporting life support systems. Energy collection could hinge on tapping low-grade heat gradients or exploiting residual radioactive decay within these icy moons or rogue planets. Communication over vast distances, too, would face major hurdles. Electromagnetic signals weaken with distance and encounters with matter or cosmic background noise, making long-range communication energy-intensive and slow. Alternative techniques might evolve, such as quantum entanglement-based communication, though current theory holds limitations on information transfer speed, or monitoring gravitational waves, which can travel unimpeded through space but require sophisticated detection apparatus. The loss of stars also means the disappearance of familiar celestial landmarks. Navigation through space, and even on planetary surfaces, becomes more complicated without visible stellar reference points. Technologies such as onboard inertial navigation, paired with gravitational field mapping or pulsar timing, using pulsars as natural cosmic clocks and beacons, could provide positional data. Pulsars, as remnants of supernova explosions, would retain their utility as reference points even in a dark cosmos, where otherwise no stars shine. Psychologically and culturally, adapting to a starless environment would be a profound shift. Humans, having evolved under the sun's cycle, depend deeply on natural light patterns to regulate metabolism, mood, and cognitive function. Removing these fundamental rhythms necessitates artificial lighting solutions, not just for illumination, but for maintaining circadian health. The design of habitats would prioritize light environments replicating day-night cycles to simulate solar rhythms, likely employing advanced LED systems capable of adjusting spectrum and intensity. Beyond individual survival challenges, the societal implications of living without stars are profound. Throughout human history, stars have been symbols in mythology, navigation, agriculture, and timekeeping. Their disappearance would require new cultural narratives and perhaps foster greater focus on internal or localized sources of meaning. The cosmological void left by absent stars might inspire new philosophies and artistic expressions oriented towards hitherto unfamiliar perceptions of space and time. The chemical implications of a starless universe extend further into the domain of matter itself. Without ongoing nucleosynthesis, elements heavier than iron, which typically form only during supernovae or neutron star mergers, would become exceedingly rare over time. These heavy elements are critical for many industrial technologies, including electronics, batteries, and specialized medical tools. As their cosmic abundance dwindles, technological development would rely more heavily on recycling and efficient reuse of existing elements. This constraint might also push civilizations to explore synthetic alternatives or novel materials, possibly engineered at the atomic or molecular level using nanotechnology or materials science breakthroughs. Quantum computing hardware, for instance, currently relies on particular elemental properties. A dearth of raw materials would challenge the production of such devices, encouraging research into less resource-dependent alternatives. At a cosmological scale, with stars extinguished and new element synthesis halted, the universe's chemical complexity simplifies. Gas clouds become depleted of their richer content and cannot form new planetary systems or organic molecules naturally. Starless galaxies, once glowing with the light of billions of stars, transform into ghosts of dust and dark remnants orbiting invisible black holes at their centers. Understanding the processes allowing life to persist in such chemically impoverished environments has driven interest in hypothetical biospheres reliant on limited chemical cycles. Such ecosystems might hinge on recycling matter to an unprecedented degree, transforming waste continuously into usable resources via engineered microbial consortia or synthetic systems. Artificial photosynthesis, simulating the natural process but powered by radioactive decay or low-level radiation instead of sunlight, could provide an ongoing source of organic molecules and oxygen for respiration. Further, hypothetical life forms might utilize alternative biochemistries more suited to the extreme cold and darkness of the late universe. For example, chemistries based on solvents other than water, such as liquid methane or ammonia found on distant icy bodies, provide potential for biological functions in cold environments. Although Earth's carbon water-based life remains our primary model for understanding these possibilities. As we look toward the far future, the eventual decline of heat-producing radioactive materials within planetary interiors is projected to occur over tens to hundreds of billions of years. Once internal planetary heating fades, even geothermal sources would wane, leaving the universe in a near-complete freeze. At that stage, only black holes hawking radiation and residual background radiation provide any measurable energy, both at levels orders of magnitude weaker than the sun's and insufficient, by known standards, to support life as we understand it. These projections outline a chilling endpoint for stellar and planetary activity, a cosmic stillness where entropies drive towards thermodynamic equilibrium dominates, and the universe reaches maximum disorder and minimal usable energy. This heat-death scenario describes a universe where no useful work or organized complexity can persist. Yet, the journey to this final state spans an almost inconceivable length of time, offering many opportunities for intelligent life to intervene, adapt, and evolve. The enormous temporal scale allows for technological development beyond current imagination, including energy manipulation methods that overcome some of today's fundamental limits, such as zero-point energy extraction or other quantum-scale phenomena. Furthermore, cosmologists continue to investigate the nature of dark energy and alternative models of the universe's fate, which could yield surprises that modify this bleak outlook. For instance, theories proposing cyclical universes or local fluctuations in vacuum energy hint at possibilities where the cosmic clock resets or new epochs emerge, potentially reigniting star formation far into the future. In sum, the persistence of stellar remnants offers pockets of complexity and energy after stars have extinguished, though these are limited and fading. The disappearance of stars marks the end of a cosmic epoch characterized by vibrant chemical and energetic cycles, replaced by a slow march toward entropy and cold. For humanity, or any intelligent being, navigating this dark era demands profound adaptations in technology, biology, culture, and philosophy. It underscores the critical dependence of life as we know it on stars, sources of energy, light, and elemental synthesis, and challenges us to imagine life and civilization thriving under radically altered cosmic conditions. Understanding the fate of these stellar remnants, their roles as future energy sources or navigational beacons, and the chemical limitations they impose, helps us map the trajectory of complexity and survival in the cosmos itself. Continuing research into extreme environments, advanced energy harvesting technologies, and new forms of life will illuminate paths for survival beyond the age of light. As such, these questions reach beyond physics and astronomy, touching the essence of what it means to endure, explore, and create meaning in a universe where the stars have fallen silent. Examining the consequences of a starless universe naturally brings us to consider the broader cosmic environment where these stellar remnants reside, namely, the ecosystems of galaxies and their ultimate fate. Today, galaxies are grand congregations of stars, gas, dust, dark matter, and other exotic matter, structured into various shapes such as spirals, ellipticals, or irregular forms. Their luminous stars serve as the engines powering not only the visual splendor we observe, but also the dynamic processes of matter formation, energy transfer, and chemical cycling critical to cosmic evolution. As stars fade and new stellar births cease, galaxies will lose the defining energy source that gives them their glowing appearance. Over tens of billions to hundreds of billions of years, their visible light will diminish until they effectively become collections of cold stellar remnants, dark matter, and sparse interstellar gas. Without the heat and radiation produced by fusion, these formerly vibrant stellar cities will drift into silence, rendering themselves increasingly invisible against the cosmic backdrop. This dimming has profound implications for structures within galaxies, including star clusters and planetary systems. Planetary systems that formed around stars prior to their extinction will face severe environmental shifts. Without their parent star's radiation, planetary surfaces will grow freezing cold, atmospheres will thin or condense, and biospheres reliant on stellar energy will collapse unless supported by alternative energy sources. Over time, collisions between stellar remnants, such as white dwarf mergers or neutron star encounters, remain occasional but rare dramatic events that can temporarily inject bursts of energy and heavier elements back into the interstellar medium. But these will dwindle as galactic materials grow exhausted. Meanwhile, the interstellar medium within galaxies, already thinning as stars consume most available gas, becomes progressively depleted. Without fresh input from supernovae or stellar winds, the supply of gas necessary for new star formation vanishes. This stagnation reinforces the cosmic aging of galaxies, transforming them into quiescent systems whose matter slowly settles into gravitational equilibrium, governed largely by dark matter's invisible halo. In the absence of active stellar populations, the gravitational interactions within galaxies take on new significance. Over time, gravitational encounters between remnants, such as white dwarfs, neutron stars, and black holes, can lead to close binary systems or even mergers. These compact binaries, particularly those involving neutron stars or black holes, can produce detectable gravitational waves, ripples in spacetime first directly observed in 2015. Such waves represent one of the few remaining dynamic phenomena in a universe without starlight, and could potentially serve future civilizations as a means of communication, sensing, or navigation. Further, the merging of massive black holes during galactic collisions releases enormous bursts of energy detectable across spacetime. Although these events become progressively rare as galaxies themselves move apart due to cosmic expansion, they demonstrate that energy release continues, albeit sporadically, long after nucleosynthesis and photon production have ceased. On even larger scales, the accelerated expansion of the universe, driven by dark energy, exacerbates the isolation of galaxies and their remnants. Distant galaxies will recede beyond each other's cosmic horizons, becoming unreachable and effectively isolated island universes. This presents a profound limit on cosmic interaction, cutting off potential travel or exchange of matter and information between galaxies. Civilizations surviving in this epoch would be confined to their own gravitationally bound galaxy or cluster, facing limited resources and no external support. Considering all this, the ultimate cosmic environment widens the challenges of survival and advancement to a galactic scale. The star's disappearance truncates the processes that continually reshape galaxies with fresh matter and energy. Over unimaginable timescales, galaxies themselves will become static, cold, and spread thin, their internal complexity declining alongside the vanishing of stellar luminosity. However, an intriguing question arises. Could advanced civilizations themselves influence or reverse parts of this cosmic decline? While stellar evolution is governed by known physical laws, future technological innovations might enable civilizations to manipulate matter and energy on enormous scales. Theoretical concepts such as stellar lifting propose that future beings might extract material from stars to extend their lifespan or artificially stimulate star formation by compressing gas clouds. Although these interventions would need to begin long before stars extinguish naturally to be effective. Similarly, large-scale astroengineering projects might create artificial stars or fusion reactors that serve as localized energy sources to replace vanishing natural stellar populations. While such undertakings remain speculative today, they underscore the possibility that intelligent life might play a proactive role in shaping cosmic futures, mitigating the harsh conditions of a starless universe by generating their own light and heat. Turning back to natural phenomena and the physical landscape of the starless cosmos, the role of low-energy radiation fields deserves attention. Before complete darkness sets in, the fading of starlight would leave behind backgrounds of infrared radiation and faint X-rays generated by remnants and residual heat. On planetary scales, weak radiation from decay and remnant objects might maintain minimal energy gradients exploitable by life forms or machines optimized for ultra-low energy conditions. More exotic radiation sources persist, such as cosmic rays, high-energy particles originating from supernovae or active galactic nuclei that, while reduced after stellar deaths, may continue at low levels. Although cosmic rays are generally a hazard to biological tissues today, future life forms or machines could utilize or shield effectively from them, possibly deriving energy or using cosmic ray signatures for communication and environmental sensing when other signals are unavailable. From a chemical standpoint, the universe entering its remnant era faces increasing scarcity not only of energy but atomic elements critical to complex structures, as noted earlier. With no new nucleosynthesis and gradual decay of materials, elemental abundances become fixed and eventually decline as radioactive isotopes decay away. This depletes the raw materials available for life, technology, and planetary geologies. In confined habitats, stringent recycling will be imperative to maintain functional ecosystems and technological infrastructures. Advances in nanotechnology and molecular-scale engineering might allow future civilizations to reconstruct molecular components from existing atoms with minimal waste, effectively closing the loop on matter usage. Such cyclical utilization could enable remarkably long-term sustainability despite external resource limitations. Moreover, energy efficiency principles would surpass today's standards by multitudes, emphasizing minimal losses and exact reuse. Any waste heat or radiation would be recycled as a resource to the greatest extent possible. This perspective challenges current human technological assumptions, envisioning a future where the scarcity of cosmic light and matter forces breakthrough innovations in energy capture, storage, and conversion. Life itself might also physically adapt or evolve to cope with the new conditions. With minimal external energy flux, biological processes would slow. Metabolism might adjust to function at low temperatures and energy inputs, possibly incorporating alternative biochemical pathways. In extremophile organisms on Earth, we already observe mechanisms allowing survival with scarce energy, and it's conceivable that in a starless cosmos, life elsewhere would develop even more radical adaptations, or rely on synthetic bioengineering designed to maximize survival. Food production systems would need to operate with artificial or low-energy photosynthesis-like processes. Bioengineered microbes or plants that convert chemical or radioactive energy directly into biomass might replace traditional photosynthesis. Closed-system agriculture designed at molecular precision could recycle water, carbon, and nutrients indefinitely, producing edible matter without sunlight. In planetary or spacecraft habitats, the absence of natural light implies extensive reliance on artificial environmental control. Architectural design might integrate bioluminescent or electroluminescent materials to simulate living conditions for inhabitants. These light sources would be calibrated to mimic natural circadian cues, enable visual perception, and maintain psychological well-being in the perpetual dark. The physiological impact of artificial lighting, particularly regarding wavelength and intensity, will be crucial. For example, blue light influences melatonin regulation and wakefulness, while red or amber light might promote relaxation or sleep. Developing lighting regimes that replicate natural cycles as faithfully as possible would help prevent disorders linked to circadian disruption, such as sleep disturbances, depression, or metabolic issues. Alongside biological considerations, psychological and social challenges emerge in living without stars. The night sky currently serves as a shared cultural canvas, inspiring religions, arts, and navigational traditions. Its sudden absence would affect human perception of place, time, and meaning. New cultural frameworks may develop around the experience of darkness, artificial light, and internal environments, possibly sparking fresh artistic and philosophical movements. Social structures and communication methods could shift toward digital or internal networks sustained within enclosed habitats. Storytelling, myth-building, and collective identity might emphasize local cohesion and histories over external celestial narratives, fostering new forms of community resilience. On a broader scale, victims of cosmic isolation due to increasing galaxy separations might cultivate deep inward-focused civilizations. Long-distance interstellar or intergalactic travel and communication become prohibitively expensive energetically and temporally, leading societies to build and maintain self-sufficient, closed systems. These enclosed societies might resemble modern concepts of generation ships, extended space habitats, or underground cities, all designed for ultimate sustainability. However, the potential for technological integration with biology, cyborg or post-biological evolution, could enable survival strategies unimaginable today. Entities augmented with artificial intelligence, robotic bodies, or virtual existence within energy-efficient computational substrates might endure conditions unsuitable for traditional, carbon-based life. Such forms could adapt their energy consumption patterns to the sparse availability, survive higher radiation, or operate in dark, cold environments indefinitely. At the intersection of technology and physics lies the possibility of exploiting new energy sources beyond traditional matter and radiation. Theoretical physics introduces the concept of vacuum energy, or zero-point energy, the lowest possible energy within quantum fields of space itself. While currently speculative as a practical source, this omnipresent energy could offer near-inexhaustible power if harnessed. Future civilizations might develop technologies that tap into quantum fluctuations, circumventing the limitations imposed by vanishing stars and matter scarcity. Similarly, mechanisms like matter-antimatter annihilation, where matter and antimatter collide to release pure energy, represent ultimate energy-dense sources. Although antimatter production is currently resource-intensive, advances could enable the synthesis and containment of antimatter in quantities sufficient to power habitats, propulsion systems, or industrial processes. Such energy might become the cornerstone for advanced life support and expansion in a universe otherwise marked by darkness. While present-day knowledge constrains our ability to predict with certainty, the interplay of dwindling natural resources and accelerating technological capability outlines pathways that could sustain complexity and life long after stars have gone out. Finally, the disappearance of starlight transforms our observational understanding of the cosmos itself. Astronomy today depends largely on detecting electromagnetic radiation emitted by stars and galaxies. In a starless universe, direct observation of cosmic structures becomes challenging. Alternative observational methods, such as gravitational wave astronomy or neutrino detection, gain prominence. Gravitational waves, as ripples in spacetime caused by accelerating masses, propagate independently of electromagnetic radiation and are less affected by intervening matter. As various compact objects, black holes, neutron stars, white dwarfs interact, they produce gravitational signals that could serve as cosmic beacons. Future civilizations might develop detectors vastly more sensitive than current instruments, enabling detailed mapping and understanding of the galaxy clusters and dark matter structures that define the universe's skeleton in darkness. Neutrinos, nearly massless particles that interact weakly with matter, also traverse the cosmos undisturbed by dust or gas. Detecting neutrino fluxes from remnants or hypothetical sources could help map energetic events invisible to electromagnetic observatories, providing insights into the underlying cosmic processes at play when visible light is no longer present. Thus, while the extinction of all stars marks the end of an epoch dominated by luminous phenomena, it opens a frontier for new means of cosmic exploration using fundamentally different signals. The universe, though devoid of light, remains rich with information encoded in gravitational and particle messengers. In conclusion, contemplating a universe where all stars have gone out leads to a deeply layered understanding of cosmic evolution, the fate of matter and energy, and the future possibilities for life and intelligence. It reveals a cosmos transitioning from active, luminous cycles to one of quiet remnants, fading radiation, and vast emptiness, posing extraordinary challenges yet also inspiring innovation and adaptation. This scenario underscores the delicate interrelation between stars and all cosmic complexity, from chemical enrichment and climate regulation on planets to biological rhythms and cultural identities on inhabited worlds. As stars flicker away over cosmic timescales, the survival of life depends on its ability to reconcile with scarcity, to harness alternative energy sources, to engineer new habitats, and to transform culturally and biologically in ways not yet imagined. Looking forward, this vision encourages reflection on our current cosmic circumstances, the imperative of sustainability, and the remarkable resilience of life amid changing environments. It also invites curiosity about what forms existence might take in the deep future, a future where humanity or its successors may navigate an endless night with ingenuity, perseverance, and a profound sense of place in an evolving universe. With the disappearance of stars, the universe's grand tapestry of light fades, and many familiar ways of knowing and navigating the cosmos vanish. Yet, even amid this profound transformation, motion and change will continue at subtle but significant levels. Understanding these dynamics becomes essential to grasping both the constraints and opportunities presented by a starless cosmos. One key feature in this nearly dark universe will be the increasing importance of gravitational interactions among stellar remnants. Without the uniform illumination provided by active stars, gravity will emerge as the principal organizer of matter on both small and large scales. Compact objects like white dwarfs, neutron stars, and black holes exert intense gravitational pulls, influencing neighboring matter and occasionally sparking transient energetic events. While the grand fireworks of supernovae and stellar births cease, interactions between remnants can still generate bursts of radiation and energy capable of sustaining localized pockets of activity. For example, when two neutron stars orbit each other in a binary system, they gradually spiral inward through the emission of gravitational waves. Eventually, they collide in a cataclysmic event that produces intense gamma-ray bursts and releases heavy elements into space. Though rare in the starless era, such occurrences might persist for an extended period, injecting fresh, albeit limited, energy and material into the cosmic environment. Similarly, the collisions of black holes, which bend and curve spacetime to extreme degrees, release gravitational waves detectable across vast distances. These ripples carry information about the masses and spins of colliding black holes and represent one of the few luminous signals persisting when electromagnetic light no longer illuminates the surroundings. Gravitational wave astronomy, a rapidly advancing field today, would remain vital to any future civilization striving to observe and understand the cosmos without stars. This shift from reliance on light-based signals to gravitational and particle-based detection rewires our conception of cosmic observation. It highlights how the universe retains a form of communication and structural complexity, even in profound darkness. Entities capable of detecting and interpreting gravitational waves, perhaps augmented by artificial intelligence and advanced sensor technology, could navigate, map, and communicate across the void, establishing networks in seemingly lifeless expanses. On smaller, planetary scales, the continued gravitational stability provided by compact remnants can help maintain the orbits of rogue planets or debris fields. These wandering worlds, cut off from stellar illumination, might still possess internally generated heat from radioactive decay or tidal stresses, as previously noted, providing isolated oases where life-supporting energy gradients persist. The gravitational influence of stellar remnants therefore acts as a skeleton on which residual cosmic order persists, despite the loss of traditional stellar energy. Importantly, gravity's unending pull means that matter will, over extended periods, tend to clump and collapse, potentially leading to new, albeit rare and exotic astrophysical processes that could temporarily counteract the overall trend toward a cold, uniform cosmos. Considering this, scientists have explored whether gravitational forces alone might under some conditions trigger cycles of compression and heating, capable of restarting nuclear fusion or similar energy-producing events in dense clouds of matter. While the likelihood of spontaneous new star formation vanishes in a starless universe due to gas depletion and expansion, rare and unusual scenarios might arise from collisions or mergers of remnants. One such phenomenon involves the merger of two white dwarfs, which could lead to a detonation resembling a Type Ia supernova. These events not only release considerable energy, but also disperse heavier elements that contribute to cosmic chemical balance. Though exceedingly uncommon in a universe long past productive stellar epochs, these flashes could punctuate the darkness with brief bursts of light and heat. Whether such events would be sufficient to sustain life or civilization gathered near them is doubtful, but their existence reminds us the universe, even in decline, does not become entirely static. Another consideration is the role of dark matter, the invisible substance that makes up roughly 85% of the universe's matter content. Dark matter does not interact with light, but exerts gravitational influence, shaping galaxy formation and large-scale cosmic structure. In a starless era, as luminous matter dims, dark matter's gravitational framework gains even more relative importance. Although dark matter remains mysterious in composition and behavior, it could potentially be harnessed as an energy or matter source in the distant future. Some speculative physics models, propose that interactions between dark matter particles might yield detectable signals or energy releases under certain conditions. While these ideas are not yet experimentally confirmed, they expand the set of possible energy regimes available beyond traditional baryonic matter tied to stars. In terms of practical survival strategies, civilizations inhabiting a universe devoid of stars might be compelled to develop technologies that convert gravitational potential energy into usable power. For instance, exploiting the energy released as matter falls into black holes, known as accretion, remains a compelling possibility. Disks of material spiraling into a black hole heat up tremendously before crossing the event horizon, emitting X-rays and other radiation. Harnessing these emissions could supply localized, intense power sources capable of supporting advanced habitats or industrial processes. Though the vast scale and scarcity of suitable material make such energy extraction a formidable engineering challenge, the enormous power densities involved make it one of the few sustainable energy options available without nuclear fusion from stars. Similarly, on planetary scales, tidal forces generated by gravitational interactions between large bodies, such as a moon orbiting a planet, could induce internal heating. On Earth and its solar system neighbors, tidal heating contributes to geological activity, as seen in Jupiter's moon Io, where volcanic activity is driven by tidal flexing due to interactions with Jupiter and other moons. This source of energy could potentially sustain subsurface oceans or biological niches on rogue planets or moons orbiting stellar remnants. Thus, gravitational dynamics become a fundamental driver of residual activity and energy in a dark cosmos. Understanding and harnessing these processes would be crucial for any civilization aiming to persist or expand when traditional stellar energy is no longer available. Turning to the nature of light itself, the absence of natural stellar illumination demands reflection on the alternative forms of electromagnetic radiation and their applications. Although visible light from fusion-powered stars would vanish, other forms of radiation, infrared, radio waves, X-rays, would intermittently persist due to residual heat emissions, remnant objects, or engineered sources. Infrared radiation, emitted by objects at low temperatures, would become a dominant illumination source, albeit faint and limited in range. Advanced detection technologies might leverage this to create navigation or communication methods relying on thermal signatures instead of visible light. Moreover, cosmic microwave background radiation, CMB, remains present throughout the universe as the remnant heat glow from the Big Bang. This radiation now peaks in the microwave portion of the spectrum at an extremely low temperature of about 2.7 Kelvin. While insufficient to support life or significant energy needs, the CMB provides a constant, uniform radiation field, a background against which the evolution of the universe can still be studied. Specialized instruments could exploit variations or interactions with this background to infer large-scale cosmic structures or physical conditions. On Earth today, radio telescopes detect various faint electromagnetic signals from distant sources. In a starless universe, detection and generation of radio waves might remain practical, especially for communication across the substantially darker environment. Radio waves can travel long distances with minimal attenuation and might become the backbone of interstellar communication technologies developed by advanced civilizations. In fact, the shift from visible light reliance to more diverse electromagnetic spectra reflects an adaptation toward exploiting all available channels of information and energy transmission in a universe in decline. Alongside natural radiation, artificial light sources will become indispensable. As previously mentioned, highly efficient LEDs or future lighting technologies able to simulate natural light spectra and cycles help maintain circadian rhythms and psychological well-being. These systems may evolve to incorporate bioluminescence, chemical processes producing light seen in some Earth organisms. As part of life support environments, reducing electrical consumption and integrating more seamlessly with ecological cycles. Considering energy conservation critically, controlling waste heat generated by artificial lighting and other systems will be crucial. In a universe increasingly cold and devoid of external heat, the release of waste heat becomes a key consideration for habitat design. Balancing heat retention to maintain livable temperatures against preventing excessive heat buildup within enclosed spaces demands sophisticated thermal regulation systems. This points toward innovations in insulation materials, heat exchange technologies, and environment control systems designed for extreme energy efficiency. Creating habitats where every watt of energy is recycled and reused maximizes sustainability and longevity in the absence of stars. As these technological and environmental challenges are met, the societal and cultural ramifications remain equally profound. The disappearance of visible stars from the night sky eliminates a long-standing source of human wonder, identity, and orientation. Future societies might develop new myths, philosophies, and artistic expressions anchored not in stellar light, but in artificial luminescence, gravitational waves, or the cold vastness itself. The loss of navigational markers provided by stars pushes spacefaring civilizations to depend on inertial navigation systems, pulsar timing, and gravitational mapping, fundamentally altering concepts of journey and place in the universe. Moreover, this shift influences perceptions of time. Without the visual cues of day and night, seasons, or celestial cycles, human temporal frameworks become artificial constructs, maintained through engineered light cycles and social agreements. These changes inevitably reshape human experience, biology, and culture over generations. Efforts to preserve or replicate the starry night might find expression in virtual reality environments or artificial dome projections, integrating science and art to sustain human connection to a cosmos without visible stars. Finally, these reflections emphasize broader philosophical themes about endurance and transformation. The extinguishing of stars confronts us with impermanence on a cosmic scale, challenging notions of permanence, familiarity, and meaning derived from the light of distant suns. Yet it also reveals the remarkable potential for adaptation, creativity, and resilience inherent in life and intelligence. The universe's most fundamental processes, gravity, quantum mechanics, thermodynamics, continue to operate, providing raw materials and mechanisms that future beings might harness in resourceful ways. Contemplating a future without stars invites a deeper appreciation of the preciousness of stellar light and energy today, while inspiring curiosity about the far future trajectories of life, matter, and consciousness in the unlit expanses awaiting beyond the ages of shining suns. Amid the profound shift from a universe illuminated by billions of burning stars to one ruled by the dim remnants of stellar death and the quiet rhythms of gravity, the concept of time itself takes on a new character. What does time mean in this deep future, when active stellar processes have faded and the universe advances toward thermodynamic equilibrium? Our everyday sense of time, tied tightly to the cycles of the sun, Earth's rotation, and seasonal changes, will be profoundly altered in a cosmos where such cycles no longer exist. At the broadest level, cosmic time continues to unfold, measured by the expansion of space and the gradual cooling and spreading of matter and energy. Yet without luminous stars serving as clocks, their pulsations, flares, and lifespans marking cosmic epochs, direct observational markers become scarce. Instead, timekeeping may rely increasingly on stable, repetitive phenomena related to compact objects. Pulsars, neutron stars that emit beams of radiation in highly regular intervals, stand out as natural cosmic timekeepers. Their pulse frequencies can be counted like a celestial metronome, providing a remarkably precise measure of temporal passage over millions of years. For civilizations existing in these later stages of cosmic evolution, pulsars could serve dual purposes, as both navigational landmarks and clocks, enabling precise synchronization of activities across spatially extended habitats. Modern astronomy already uses pulsar timing to probe gravitational waves and test general relativity, indicating their utility even in our current era. In a universe without visible stars, pulsars' rhythmic signals would be invaluable beacons amid the darkness. On smaller scales, planetary or habitat-sized, artificial timekeeping will assume a primary role. Mechanical, atomic, or quantum clocks, perfected through successive technologies, would regulate daily and longer-term cycles in the absence of natural environmental cues. Societies would deliberately construct cycles of day and night through artificial lighting, temperature shifts, and scheduled activities to mirror fundamental biological and psychological needs. Yet the absence of predictable celestial cycles might pose challenges for longer-term calendars and historical memory. Without stellar phenomena demarcating years or seasons, timekeeping systems would be entirely human-made, potentially varying between isolated communities or habitats. This cultural fragmentation of time perception highlights a deep connection between cosmic events and human cognition. Beyond timekeeping, the fundamental nature of information and communication over cosmic distances becomes increasingly critical in a starless universe. The vast expanses between stellar remnants and isolated systems demand efficient, robust transmission methods for messages, coordination, and the potential sharing of knowledge or consciousness. Electromagnetic communication, while effective over great distances, requires substantial energy and is subject to signal degradation and delay. Recent advances in quantum information science may offer alternative strategies. Quantum entanglement, for example, establishes correlations between particles separated by arbitrary distances. Though it cannot be used for faster-than-light communication, entanglement-based protocols, such as quantum teleportation or quantum key distribution, enhance information security and error correction. Over immense timescales and distances, engineering such quantum networks might become a cornerstone of interstellar or intergalactic information exchange, preserving cultural continuity and technological knowledge long after starlight fades. Another promising avenue involves gravitational wave communication. Unlike electromagnetic waves, gravitational waves pass unimpeded through matter and can traverse cosmic distances with little attenuation. Hypothetical civilizations might develop technology capable of generating and detecting modulated gravitational signals. Though currently beyond our technological reach, these methods could revolutionize communication in a dark, starless cosmos where traditional electromagnetic beacons are sparse. On planetary and habitat scales, the challenges of resource management will escalate dramatically as accessible raw materials become scarcer. Mining and manufacturing technologies must evolve to operate with minimal waste and maximal recycling efficiency. Material extraction without stellar energy inputs, such as sunlight to assist chemical processes or heat, demands alternative energy sources, primarily nuclear, geothermal, or mechanical energy harnessed from gravitational interactions. Synthetic biology and nanotechnology could play pivotal roles here. Engineered microorganisms or molecular machines might facilitate closed-loop recycling of materials at microscopic levels, breaking down waste products into elemental forms and reassembling them into structural components, machinery, or food precursors. Such processes mimic natural biogeochemical cycles, but are likely to operate at unprecedented efficiencies and control. Furthermore, the development of self-repairing materials and adaptive systems capable of adjusting to wear and environmental stresses would lengthen the operational lifetimes of infrastructure and habitats. Reducing breakdowns and minimizing maintenance requirements are key strategies to stretch diminishing resource stocks over millennia or longer. Climate and environmental control within habitats will also reach extraordinary precision and sophistication. As external conditions remain perpetually cold and dark, internal systems must manage air composition, humidity, temperature, and radiation shielding with minimal energy expenditure. Advances in artificial photosynthesis or chemical energy storage might enable habitats to generate oxygen and organic compounds independent of external inputs, reducing reliance on imported materials or energy sources. Alongside physical necessities, the cultural and philosophical dimensions of life in endless darkness will become increasingly important. Human beings derive much of their meaning and orientation from engagement with the cosmos. The stars, the sun, the night sky. Their removal forces fundamental reconsiderations of identity, place, and purpose. New narratives could arise rooted instead in technological mastery, communal resilience, or exploration of less visible cosmic phenomena such as gravitational waves or neutrino events. Artistic expressions might integrate advanced virtual realities simulating lost celestial vistas, preserving ancestral memories of starry skies and cosmological cycles. Alternatively, art, religion, and philosophy might shift focus inward, emphasizing the internal experiences of consciousness and community amid a silent, dark universe. Such shifts would be gradual, reflecting the slow fading of starlight over cosmological timescales. However, they highlight the interconnectedness of cosmic phenomena with human culture, suggesting that the fate of stars is not merely a matter of astronomy, but also deeply entwined with the evolution of civilization itself. In discussions of survival strategies, one final frontier comes into focus: the prospects for transcending biological forms entirely. As conditions grow increasingly inhospitable for carbon-based life, transforming consciousness into digital or otherwise non-biological states becomes a compelling possibility. Such post-biological entities may operate with drastically reduced energy needs, enhanced durability, and the ability to exploit exotic energy sources unavailable to organic beings. For example, computational substrates cooled to cryogenic temperatures can, in principle, function with minimal thermal noise, extending operational lifespans dramatically. These forms of machine life could integrate closely with the gravitational, quantum, and exotic energy sources present in the late universe, forming civilizations well adapted to the new cosmic environment. In this vein, even the expansion of intelligence beyond local habitats into the vast dark spaces between remnants could become feasible. Autonomous probes or artificial intelligences powered by quantum vacuum energy or black hole accretion emissions might explore and maintain networks in starless voids. While these concepts remain speculative now, they derive naturally from the conditions imposed by a universe bereft of living stars. Necessity driving innovation toward forms of existence radically different from those we know. Overall, the implications of a starless cosmos extend far beyond the astrophysical phenomena of stellar death and radiation cessation. They ripple through human biology, technology, culture, philosophy, and the very definitions of life and time. Studying this distant future helps illuminate the delicate balances sustaining life today, and fosters the imagination needed to envisage survival, meaning, and transformation when the light of the stars finally fades. As the stars vanish and the cosmos grows steadily darker, the need for new forms of energy production and management becomes more urgent than ever. Just as today humanity harnesses the sun as its primary energy source, future civilizations facing a universe without stars would have to lean heavily on alternative, non-stellar energies, pushing both scientific innovation and engineering to unprecedented scales. One of the more immediate and feasible contenders in this energy search is nuclear fusion powered not by the gravitational collapse of stars, but artificially ignited on demand within carefully engineered reactors. Fusion reactors seek to emulate the reactions that once powered stars, but within contained environments on planets or spacecraft. Though fusion power remains a challenge currently, progress in magnetic confinement or inertial confinement techniques offers hope of stable, long-lasting energy sources independent of sunlight. In a starless universe, such reactors would likely become vital hubs of power generation, sustaining habitats, industrial processes, and even propulsion systems. Alongside fusion, fission reactors, already a mature technology today, would continue to play a central role. Natural radioactive materials such as uranium and thorium would provide compact, dense energy supplies capable of running for millennia, especially if breeder reactor designs allow efficient use and recycling of fuel. However, the limited abundance of fissile materials imposes a hard constraint. Future societies would have to optimize recycling and careful resource management rigorously to stretch supplies. Aside from nuclear processes, thermal energy generated from gravitational interactions offers another source potentially exploitable for survival. The tidal forces exerted by binary systems of compact objects, or the gravitational flexing of moons orbiting massive bodies, produce internal heating manifested as geological activity, as we see in moons like Io and Europa today. Such energy can maintain subsurface oceans or warm planetary interiors, offering stable ecological niches despite the absence of stellar heating. Harnessing this form of gravitational energy would require sophisticated technologies to extract heat efficiently from planetary interiors and convert it into usable electricity or thermal conditions suitable for life support. Concepts such as geothermal power plants operating on hostile, cold worlds might be extended to operate near or beneath ice shells, where heat gradients persist. Additionally, mechanical energy derived from planetary rotation or orbital motions could be converted via advanced electromechanical systems, assuming those rotations remain stable over long durations. At the largest scale, black holes emerge as enigmatic but potentially significant energy reservoirs. While commonly perceived as purely destructive entities, black holes' interactions with surrounding matter produce intense energetic phenomena. Accretion disks, the swirling material consuming black holes, heat up to millions of degrees Kelvin, emitting high-energy radiation and powerful jets. Developing technologies to capture and convert this energy into usable power represent a potentially game-changing prospect for civilizations in the deep cosmic dark. Though engineering challenges are daunting, such as stabilizing orbits near event horizons and managing extreme tidal forces, the reward is potentially enormous energy densities. Moreover, the slow Hawking radiation emitted intrinsically by black holes, while feeble in stellar mass black holes, becomes more prominent as black holes evaporate over unfathomable timescales. If advanced societies could amplify or concentrate this radiation, it might serve as a stable energy trickle after all other sources decline. Beyond physical energy sources, the management and manipulation of information become a crucial frontier in a dark cosmic age. With energy scarce and communication across vast distances hindered by expansion and fading signals, preserving knowledge, culture, and coordination assumes paramount importance. Strategies could include highly durable, error-correcting information storage systems designed to withstand long periods without maintenance, or decentralized knowledge networks distributed across habitat clusters to prevent localized loss. In this context, artificial intelligence and autonomous systems may serve as custodians of civilization, maintaining operations, repairing infrastructure, and managing resource cycles with minimal human intervention. AI could also assist in exploring and exploiting subtle energy gradients and environmental changes, identifying and optimizing emergent resources in an environment where visible markers are few. Long-duration memory storage poses unique challenges. Conventional media degrade over decades or centuries, but futuristic approaches such as molecular or atomic-scale data encoding, using stable crystal lattices, synthetic DNA, or quantum states, might extend information retention over millions or billions of years. Such longevity is essential when communication delays stretch across light years, and when technological renewal is slow or impossible. On the societal level, managing human psychology in the absence of natural, day-night cycles and starry skies entails creating artificial environments that preserve the psychic and physiological health of inhabitants. Advanced architectural designs might emulate natural settings using dynamic lighting, that mimics solar intensity and color variation, soundscapes simulating natural phenomena, and temperature modulation to mark temporal cycles. These environments would help mitigate effects like circadian rhythm disorders, depression, and social fragmentation. Moreover, cultural adaptation to a starless sky would likely foster new art forms, philosophies, and communal narratives centered around inner light, memory, and cosmic solitude. Virtual reality could allow individuals to experience reconstructed star fields, historical cosmic events, or even imagined stellar phenomena, supporting a connection to a universe lost to direct observation. Such immersive experiences would serve not only leisure and mental health, but also education and cultural transmission. Another critical adaptation involves food production in the near absence of solar input. Current agriculture depends heavily on photosynthesis powered by sunlight, and its absence would require radical alternatives. Artificial photosynthesis, the replication of plant light harvesting chemistry through engineering, coupled with artificial lighting, could produce oxygen and biomass necessary for closed ecological systems. Alternatively, chemotrophic organisms leveraging chemical energy sources or engineered food synthesis via molecular manufacturing could supplement or replace traditional agriculture. Hydroponic or aeroponic farming techniques, already improving Earth's food efficiency, would be indispensable components of habitat ecosystems. Coupled with recycling systems for water, nutrients, and waste, these methods could maintain crop cycles indefinitely within closed habitats. Microbial consortia designed for nutrient cycling and soil regeneration might operate in tandem with engineered plants or synthetic foods. Looking outward, the prospects of interstellar travel or migration must be re-examined in a universe where stars have gone dark and distances expand relentlessly. With no luminous targets to guide by and extremely limited energy sources, navigation and propulsion face severe constraints. However, local gravitational beacons such as pulsars or the faint electromagnetic emissions of stellar remnants might serve as reference points. Propulsion systems that recycle energy internally or harness external gravitational fields, such as gravitational slingshots around dense objects, could maximize efficiency. Beamed energy propulsion, using lasers or particle beams from compact habitats or neighboring remnants, might supplement onboard fuel, enabling gradual migration between gravitationally bound systems. Such movements, while slow, might serve as survival strategies, allowing civilizations to relocate to remaining resource-rich niches, such as planets orbiting white dwarfs still cooling or reservoirs warmed by tidally heated moons. Yet the limitations of speed and the isolation imposed by cosmic expansion mean migration will only be practical on relatively local scales within gravitationally bound clusters. At the cosmological scale, dark energy's continued acceleration of universal expansion creates an event horizon beyond which objects recede faster than light, becoming causally disconnected. This isolates star systems and their remains into island universes, beyond which communication or travel is effectively impossible. Consequently, survival and development become even more localized, reinforcing the need for efficient resource management and closed system sustainability. Within such isolated pockets, civilizations might increasingly turn inward, focusing on habitat optimization, longevity technologies, and virtual or enhanced consciousness experiences. This inward turn may foster cultural evolution emphasizing resilience, adaptation, and existential meaning, divorced from external cosmic landmarks. In reflection, the enduring march toward a starless universe compels us to reconsider the fundamental relationship between energy, life, and knowledge. Our current cosmic environment, illuminated by countless stars, not only sustains life but shapes our biological rhythms, cultural narratives, and scientific inquiry. Its eventual extinction magnifies the fragility and preciousness of these conditions. Yet, as we consider the distant future, the potential for adaptation through technology, culture, and biology shines through. the ability of life to inhabit dark ocean depths, the resilience of microorganisms thriving in radioactive environments, and humanity's relentless innovation give grounds for cautious optimism. Even in a cosmos devoid of natural starlight, complexity and consciousness may find ways to endure. Ultimately, imagining a universe without stars expands our understanding of survival beyond familiar conditions, challenges assumptions about the necessity of light and warmth, and invites us to explore how life and intelligence might persist through creativity and perseverance when all else grows dim. The journey toward that distant time encourages reflection on our present place in the cosmos and inspires the technologies and philosophies that may one day sustain civilizations amid eternal darkness. As we explore the eventual loss of stars and the deep cosmic darkness that follows, it's natural to ask, what might the universe look like on the largest possible scale when only the faint remnants of stellar activity remain? Without the energetic light of stars, the familiar cosmic patterns we observe today, the luminous swirls of spiral galaxies, the bright clusters within galaxy groups, would fade into near invisibility. This raises important questions about the fate of large-scale cosmic structures and how the expansion of space will influence them. Current cosmological observations reveal that our universe is not static. It is expanding, and intriguingly, this expansion is accelerating due to a mysterious force known as dark energy. This accelerating expansion has profound consequences in a starless cosmos. Over immense timescales, galaxies that are not gravitationally bound to each other will drift farther apart, eventually crossing what physicists call a cosmic event horizon. Beyond this horizon, objects recede faster than light relative to us due to the expansion of space, making any signals they emit impossible to detect or receive. As the stars themselves fade and galaxies lose their light, this cosmic isolation grows more pronounced. Clusters of galaxies that remain gravitationally bound may continue to orbit and interact, while the rest of the universe beyond these clusters appears as an ever-darkening void. This isolation effectively walls off regions of the universe from one another, limiting the exchange of matter, energy, and information. The eventual result of this process is a set of island universes, discrete pockets where matter and remnants coalesce against the backdrop of an ever-expanding, dark and cold cosmos. Within each island, the interplay of gravitational forces among dense stellar remnants and dark matter will shape the residual structure, while the broader cosmos fades into ghostly silence. The consequences for surviving civilizations or life forms within such an island universe are immense. The cosmic isolation reinforces the necessity of self-sufficiency. No external aid, resources, or information would arrive from beyond the gravitationally bound local group. All resource recycling, energy production, and technological innovation would have to occur entirely within the constraints of a finite, isolated system. Turning to the material composition of these island universes, over extraordinarily long periods, even dense matter faces decay. Though ordinary matter is generally considered stable, certain particles such as protons might decay over unimaginably long timescales according to some theories, still unconfirmed experimentally. If proton decay occurs, it would cause even stable atomic matter to disintegrate gradually, further limiting resources and complexity. Alternatively, if protons withstand decay, matter persists longer but still faces energetic challenges due to entropy and loss of usable energy gradients. In tandem with particle decay considerations, the abundance and distribution of dark matter become critical. While dark matter's precise nature remains a mystery, it dominates the gravitational architecture of galaxies and clusters. Its persistence in the starless era implies that it continues to shape local gravitational wells, influencing the behavior and stability of matter within island universes. Some speculative proposals envision future civilizations harnessing dark matter directly or indirectly, perhaps by detecting weak interactions or manipulating gravitational potentials it creates. Whether such endeavors are feasible depends on fundamental particle physics discoveries yet to come. On the subject of fundamental physics, one natural question is whether the physical laws themselves might yield new forms of energy or structure as the universe evolves toward extreme cold and low densities. Processes associated with quantum vacuum fluctuations, the spontaneous and temporary appearance of particle-antiparticle pairs in empty space, may offer subtle energy flows. Though currently inaccessible with known technology, future advancements in quantum engineering might enable tapping into these fluctuations as an energy source, turning the vacuum of space itself into a reservoir for sustaining processes in an otherwise dead universe. From a different angle, the thermodynamic principle known as the second law states that entropy, the amount of disorder, must increase over time in a closed system. In cosmic terms, this means the overall usable energy diminishes, rendering the universe progressively less able to sustain organized structures or life. However, the enormous timescales involved allow local decreases in entropy, such as habitats or structures maintained through input energy, even as global entropy rises. Consequently, engineered systems that recycle energy with exquisite efficiency might extend periods of low entropy locally, supporting life and technology for durations far beyond those achievable under current natural conditions. This concept places heightened emphasis on breakthrough technologies in energy conversion, waste heat recycling, and matter conservation. From the perspective of chemistry and materials science, the absence of stellar nucleosynthesis halts the formation of new elements, but long-lived isotopes and stable elements will remain. Extracting maximal utility from these resources in isolated habitats challenges future chemists and engineers to develop materials with minimal degradation and maximal recyclability. Advances in atomic-scale fabrication and quantum chemistry could yield materials and devices able to repair themselves or be transformed repeatedly, defying wear in the hostile environment. In parallel, alternative solvent systems and chemistries beyond the familiar terrestrial ones might be explored to utilize exotic environments within island universes. For example, solvents such as liquid methane or ammonia, stable at low temperatures common in these epochs, could support forms of chemistry and potentially life adapted to much colder conditions than Earth organic life. While speculative, this broadens the range of possible habitats for life and technology in the starless future. Considering all these factors, the scale at which survival attempts might be made shifts from planetary or stellar systems to the scale of galactic clusters or isolated gravitationally bound systems. This scale provides the resources and structures necessary to maximize the duration and complexity of life or civilization. On an even grander scale, some cosmological models propose that the accelerating expansion driven by dark energy may itself change in character over vast timescales. Concepts such as the Big Rip scenario predict that dark energy's intensity increases without bound, eventually tearing apart even atoms and subatomic particles. Other models suggest a more gently evolving or cyclic universe, where phases of expansion and contraction repeat on scales far beyond current observation. Should such scenarios prove accurate, the ultimate fate of matter, energy, and life would be profoundly altered. In the former case, all structure is destroyed in a cataclysmic event. In the latter, new cosmic epochs and potentially new star formation cycles might arise far in the future. While speculative and unsettled, these models underscore our incomplete understanding of cosmic destiny and point to the continuing role of fundamental physics in informing the narrative. Returning to practical concerns for survival, the island universe structure emphasizes the potential importance of long-term energy storage and transport technologies. Given that the input of fresh energy from outside sources becomes impossible, civilizations must develop means to store energy across geological or even cosmological timescales. Promising approaches include advanced superconducting materials to store electrical energy with minimal losses, or dense chemical energy storages tailored for longevity. Furthermore, harnessing gravitational waves, or neutrino fluxes for communication within an island universe, offers intriguing though technically challenging possibilities given their low interaction rates. For exploration and potential rescue missions, robotic probes or autonomous artificial intelligences operating within such contexts would need to navigate without stellar landmarks, relying on gravitational mapping or pulsar timing. The development of reliable, redundant navigation systems insensitive to cosmic-scale disruptions is critical. Finally, considering the cultural and philosophical dimensions of life confined to island universes offers profound reflections. The loss of access to the wider cosmos, no new information or contact beyond gravitational horizons, places a premium on the preservation of knowledge, the cultivation of meaning within limited domains, and the psychological adaptation to cosmic isolation. Communities may develop intricate mythologies or cosmologies rooted in the structure and history of their island, oriented around the faint but persistent signals from pulsars, black hole jets, or gravitational wave events. These phenomena, scarce yet reliable, could serve as both navigational aids and symbolic beacons. In conclusion, the formation of isolated cosmic islands as the universe darkens and expands defines a new frontier for life, intelligence, and civilization. These vast yet finite domains press living systems to evolve resilience, self-support, and ingenuity on unprecedented scales. While stars vanish and traditional lights of the cosmos fade, rich and dynamic processes driven by gravity, quantum phenomena, and the remnants of matter persist, offering arenas where life could adapt and perhaps even flourish in the deep future. This perspective highlights the profound interplay between cosmic evolution and the very possibility of persistence, a dance between entropy and order, isolation and connection, darkness, and the ingenious spark of life. Far from signaling an absolute end, the disappearance of stars marks the beginning of a new and deeply challenging chapter in the universe's story, one where survival hinges on mastering the subtle energies and the immutable laws shaping the island universes that remain. Within these isolated island universes, the enduring dominance of dark matter and black holes raises important questions about their roles not just as cosmic architects, but as potential resources or even environments for future civilizations. Dark matter, while elusive in its physical nature, shapes the gravitational landscape underlying all visible matter. Its gravitational wells effectively sculpt the clumps of matter that form galaxies and galaxy clusters, anchoring the matter we interact with. From a practical standpoint, the omnipresence of dark matter means that even in these isolated pockets, the overall gravitational environment remains dynamic and complex. Although dark matter does not emit or absorb light and interacts very weakly with ordinary matter, its gravitational pull influences the stability and dynamics of stellar remnants and planetary systems that persist after the star formation era fades. This persistent gravitational scaffolding ensures that the matter and resources within an island universe do not disperse indiscriminately, but retain organization suitable for habitat construction and resource management. While direct interaction with dark matter remains hypothetical, future civilizations might develop technologies that exploit gravitational potentials created by dense concentrations of dark matter. For example, adjusting orbital pathways using gravitational assists within these potentials could optimize energy efficiency for locomotion or resource extraction within their local environment. In more speculative physics, if dark matter consists of particles with small but non-zero interactions, advanced technologies might even catalyze or harness those properties to produce usable energy or information carriers. Turning to black holes, these enigmatic objects are not merely cosmic graveyards, but repositories of immense energy and information. Beyond being endpoints of stellar evolution, black holes actively influence their surroundings. Accretion of matter onto black holes converts gravitational potential energy into high-energy radiation and relativistic jets, providing concentrated energy bursts in an otherwise dark cosmos. For civilizations confined to an island universe, managed harnessing of such energy sources could be critical. The engineering challenge of living near black holes is formidable. The extreme gravity gradients near event horizons impose harsh tidal forces and intense radiation environments. Yet the potential energy yields are extraordinary. Matter spiraling into a black hole converts up to tens of % of its mass energy into radiation prior to crossing the point of no return, a vastly more efficient process than nuclear fusion within stars. Devices such as Dyson spheres or scaled-down versions might be constructed around stable accretion disks or Kerr black holes, rotating black holes, to capture emitted energy. Moreover, black holes themselves might serve informational or computational functions for advanced civilizations. The theoretical connection between black holes and holographic principles in physics hints at profound relationships between their event horizons and information storage. In the far future, it is conceivable that intelligent beings might integrate black holes into computational substrates or data storage, transcending conventional matter-based hardware, thereby operating within environments inhospitable to biology, but accessible to artificial intelligence. On a related front, the gradual evaporation of black holes via Hawking radiation, missing as an active energy source today, but becoming more significant over trillions of years, offers a persistent, albeit faint, energy output. Harnessing this radiative trickle would be extremely challenging, but could provide steady, long-term power beyond the expiration of other sources. Beyond the gravitational and energetic landscape, understanding the chemical and material environment within island universes remains essential. Over cosmic epochs, large-scale chemical complexity declines as nucleosynthesis halts and existing heavy elements decay or become locked away in inert forms. Nonetheless, atoms composing planets, remnants, and potential habitats endure. The key to sustaining complex life or technology lies in preserving, recycling, and efficiently repurposing these finite material resources, emphasizing closed-loop ecological and industrial systems. With the disappearance of stellar fusion creating new elements, future societies must contend with material scarcity akin to increasingly severe resource depletion scenarios seen on planetary scales today, but elevated to cosmic proportions. Such scarcity drives innovation in materials science, recycling technology, and synthetic biology, enabling maximum utility from every available atom. Nanotechnology might reach profound levels of precision, assembling structures atom by atom and repairing material degradation at the molecular scale, prolonging operational lifetimes indefinitely. Molecular machines could catalyze the conversion of waste back into foundational elements or complex compounds, tackling chemical degradation and entropy locally. Simultaneously, habitat design adapts to these constraints. In subterranean or enclosed habitats on rogue planets or moons orbiting compact remnants, construction materials would need extreme durability and radiation resistance, protecting inhabitants from cosmic rays and particle flux. Self-healing composites and responsive environmental control would maintain structural and life support integrity over immense durations. Extending the concept of habitat environments, the shift toward cold, dark conditions enforces rethinking of life's biochemistry. Terrestrial life relies heavily on liquid water as a solvent in carbon-based chemistry optimized for moderate temperatures maintained by sunlight. However, in legacy starless environments, surviving life must confront near-freezing or cryogenic conditions, pushing toward alternative biochemical paradigms. Though speculative, biochemistries based on solvents like liquid methane or ammonia, stable at much lower temperatures, could enable metabolism at cryogenic temperatures that would be lethal to current Earth life. On Titan, Saturn's largest moon, and in other icy bodies, such cold chemistry remains an active area of astrobiology research. If life or engineered organisms can function at such extremes, they expand the survivable niches within island universes beyond the traditionally conceived habitable zones. For humanity or its descendants, artificial biotechnologies might recreate or enhance these alternative biochemistries, or engineer pluripotent organisms customized for starless, cold habitats, capable of metabolizing sparse chemical energy sources derived from geothermal or radiogenic processes. This would be a paradigm shift in biology, turning the former limits of life into new frontiers. From an informational perspective, the absence of stars also transforms navigation and observational astronomy. Today's methods rely heavily on visible starlight, but in a starless future, alternative cosmic signals would dominate navigation. Pulsar timing arrays, gravitational wave mappings, and neutrino observatories become the cosmic GPS. Pulsars, with their highly stable rotational periods, provide natural timing and spatial reference points, fundamental for synchronization across habitats and fleets. Gravitational wave detectors, possibly vastly advanced variants of instruments like LIGO or future space-based arrays, could trace the mergers and motions of dense remnants, enabling mapping of gravitational landscapes. Neutrino emissions, though exceedingly faint and rare, offer another observational channel passing unimpeded through matter, providing insight into ongoing processes within compact objects or accretion phenomena. This multi-messenger approach to cosmic observation, combining gravitational waves, neutrinos, and residual electromagnetic signals, would mark a distinct observational era, redefining humanity's relationship to the cosmos itself. Intelligent beings living in deep darkness would, in effect, hear and feel the universe's structure rather than see it, stimulating new scientific paradigms and technologies. Such shifts in sensory engagement would influence not only technology but culture and philosophy. Human imagination and expression have long been linked to the star-studded night sky. The absence of visible stars would necessitate new cultural anchors, perhaps grounded in the rhythms of pulsars, the hum of gravitational waves, or the subtle glow of black hole emissions. Art, religion, and narrative could revolve around the intangible phenomena that still permeate the dark cosmos, fostering fresh aesthetic and spiritual experiences aligned with new cosmic realities. Psychological health in entirely artificial environments also becomes a prime concern. Without natural day-night cycles or visual horizons, engineered habitats must embed comprehensive sensory stimuli mimicking natural variation. Light intensity spectra, soundscapes, temperature cycles, to sustain circadian biology and psychological well-being. Virtual reality and neural interfaces might augment these stimuli, allowing individuals to experience recreated star skies or even entirely novel sensory environments beyond human evolutionary experience. Lastly, considering the ultimate long-term future, the prospects for survival revolve around the mastery of increasingly subtle and exotic energy sources. As all natural stellar and remnant energies dwindle, advanced civilizations may turn toward harnessing vacuum energy, zero-point fluctuations, or other emergent quantum phenomena. While purely theoretical at present, the controlled extraction of energy from the quantum vacuum could, in principle, provide an inexhaustible reservoir powering computation, life support, or even cosmic engineering projects. Similarly, matter-antimatter reactions, if low-energy antimatter production and storage become technological realities, offer density and efficiency unparalleled by any current energy source. Storage of antimatter and controlled annihilation could sustain habitats or propulsion with minimal mass and volume, critical as material resources become constrained. In this far future, digital or post-biological forms of existence may dominate, tailored to operate with minimum energy in cold, dark environments, exploiting quantum computation and vacuum energies beyond the capacities of organic life. In conclusion, the universe's transition from a vibrant era of shining stars to a dark age of remnants and isolation, brings profound challenges and remarkable opportunities. The emergence of island universes formed by gravitationally bound matter sets the stage for survival in a harsh yet structured environment dominated by gravity, quantum processes, and engineered ecosystems. Throughout this journey, life and intelligence would confront scarcity, isolation, and entropy, responding with adaptation, ingenuity, and the transformation of biology, technology, and culture. While the death of the stars marks the end of familiar cosmic patterns, the persistence of gravitational forces, exotic residues, and quantum realms keeps open the possibility for new forms of complexity and existence, lighting the way in an otherwise dark universe. Given the increasingly isolated nature of these island universes and the fading of traditional stellar energy sources, a critical focus turns to the concept of longevity, not just of individual habitats or species, but of information, technology, and culture itself. The challenge of sustaining knowledge and continuity across vast timescales becomes a cornerstone for any civilization striving to endure in a cosmos bereft of stars. Without regular input of new resources, and with communication horizons shrinking steadily, preserving accumulated wisdom and technological capability demands systems designed for both resilience and adaptability. One strategy involves the development of ultra-stable information storage technologies that resist the ravages of time and radiation. Unlike contemporary media such as magnetic disks or solid-state drives, which degrade on the order of decades or centuries, future civilizations might encode information at atomic or even subatomic scales. Synthetic diamond lattices, crystalline structures engineered for error correction, or molecular chains that self-repair could serve as repositories capable of retaining data intact over billions or trillions of years. In astrophysical terms, information encoded at such densities could outlast many natural processes and be retrievable even after long periods of exposure to cosmic radiation. Moreover, redundancy would be a key aspect of long-term data preservation. Copies of critical knowledge could be distributed across multiple isolated habitats, embedded deep underground, or stored on inert bodies like asteroids or dormant planets, shielding it from local catastrophes. This dispersal mimics the resilient strategies seen in biological systems and human cultural practices, where the duplication and geographical spread of information enhance survival probability. Beyond passive storage, the active management of knowledge involves autonomous or semi-autonomous systems, advanced artificial intelligences capable of continual maintenance, error checking, and adaptation to changing environments. These AI custodians would oversee the health of storage media, initiate repairs, and update content as needed, possibly even rediscovering lost techniques or optimizing systems in response to unforeseen circumstances. In epochs when humans or other organic beings are limited in numbers or absent, such digital stewards might serve as the continuators of civilization's legacy, ensuring that critical information endures until conditions allow transmission or revival. Turning to the preservation of culture and identity, future societies will face particular challenges rooted in the absence of natural celestial reference points. Without stars to orient navigation, calendar systems, and symbolic meaning, communal coherence will rely heavily on constructed frameworks. Artificial cycles denoting days, months, or years must be maintained to regulate social and biological rhythms. These timekeeping mechanisms might be synchronized to pulsar timings, highly consistent cosmic clocks, or internal atomic clocks, lending a subtle yet profound astrophysical connection to the cosmos despite the loss of visible stars. Historically, human cultures have integrated celestial phenomena deeply into their rituals, myths, and worldview. The disappearance of these touchstones calls for new narratives grounded in local environments, technological achievements, or the subtle cosmic signals still accessible. For instance, pulsars' rhythmic pulses might become central cultural icons, symbolizing continuity and order in the cosmic void. Similarly, gravitational wave events marking black hole mergers could inspire storytelling, art, or calendrical markers, reflecting an evolved human relationship with the universe that emphasizes listening and sensing rather than seeing. The psychological adaptation to an overwhelmingly dark environment also implies the necessity for immersive virtual and augmented realities. These technologies could reconstruct the lost splendor of starry skies or simulate familiar natural phenomena, providing inhabitants emotional and cognitive anchors essential to mental health. Over prolonged durations, the ability to create and engage with such synthetic environments may be as critical as physical survival, counteracting the isolating effects of perpetual darkness and confinement. Expanding beyond information and culture, the physical infrastructure sustaining life in a starless universe hinges on continuous energy management and efficient recycling of matter. Without stars replenishing energy and raw materials, habitats must employ stringent closed-loop systems that recover and reuse every resource. Water, carbon, nitrogen, and other vital elements must circulate indefinitely through engineered ecosystems, mimicking Earth's biogeochemical cycles, but at an elevated level of precision and control. These systems could incorporate biological, chemical, and mechanical components operating synergistically. Engineered microbes specialized in waste breakdown and nutrient generation, coupled with synthetic plants or artificial photosynthetic devices powered by nuclear or geothermal energy, would maintain food production and oxygen supplies. High-efficiency filtration, solid-state waste converters, and molecular assemblers might manage materials from plastics to metals, disassembling used parts at the atomic level and rebuilding needed components as required. The challenges in perfecting such regenerative life support systems are immense, especially considering the threats posed by system errors or failures that could cascade and compromise habitat viability. Therefore, incorporating redundancy, fault tolerance, and self-repair mechanisms is paramount. Future habitats might also feature distributed processing and control, where multiple independent systems continuously validate each other's performance, ensuring stability over long timescales. On the energy front, nuclear processes remain the most promising staple for sustaining closed habitats. Fusion reactors, if successfully engineered for stable operation, could deliver massive amounts of power with low radioactive waste. Fission reactors, especially advanced breeder designs, could recycle fuel effectively for millennia. Tapping gravitational energy through orbital dynamics, tidal heating of moons or planets, and even mechanical energy conversion might supplement these primary sources. As black holes persist as ultimate long-term energy sources, the prospect of harnessing their accretion disks or Hawking radiation becomes even more compelling. While engineering such energy extraction systems involves daunting technology, operating near extreme gravity and radiation environments, the potential payoff is enormous, enabling continuous power supply after all other sources decline. Given energy scarcity, conservation and efficiency reach new strategic heights. Future technologies would minimize waste heat, recycle irradiated materials, and optimize energy usage for life support, computing, and transportation. Low-power electronics, superconducting circuits, and quantum computing architectures could reduce energy footprints dramatically, extending the operational lifespan of habitats and autonomous systems. In parallel, habitat design will emphasize insulation and environmental control, maintaining stable internal conditions despite external temperature extremes close to absolute zero. Adaptive materials that adjust thermal conductivity, radiation shielding that protects from cosmic rays, and modular architecture allowing flexible reconfiguration and repair will be essential. Beyond physical constraints, social structures face equally formidable hurdles. Communities isolated on planets, moons, or space stations with no natural external communication pose risks of social fragmentation or stagnation. Maintaining social cohesion, diversity, and motivation over generations or millennia necessitates deliberate cultural engineering. including education systems geared toward fostering cooperation, adaptability, and psychological resilience. Technology may assist here as well through virtual environments, immersive storytelling, and continuous participatory social frameworks encouraging shared goals and identity. The sense of stewardship over knowledge, environment, and future becomes a critical psychological anchor in this context, motivating collective action toward survival. Another domain of importance is biological adaptation. Human physiology evolved under Earth's conditions, regulated by circadian rhythms synchronized to sunlight, and protected by natural magnetospheres and atmospheres moderated by solar energy. Long-term survival in artificial, closed habitats demands biomedical interventions to address the lack of ultraviolet radiation for vitamin D synthesis, adjusted light exposure to sustain circadian cycles, and countermeasures against muscle atrophy and bone density loss from altered gravity conditions. Genetic and epigenetic therapies could enhance adaptability, mitigating some effects of living in artificial, lightless environments. Moreover, bioengineering might develop novel symbiotic organisms or biomechanical enhancements tailored to habitat conditions, further intertwining technology and biology. Looking outward, despite the vast expansion and isolation of island universes, localized exploration and migration remain conceivable within gravitationally bound groups. Robotic probes or crewed missions powered by nuclear or exotic propulsion systems could travel between remnant systems, seeking resource-rich planets, moons, or other habitats supported by geothermal or accretion energy. Navigation within this environment relies heavily on pulsar timing and gravitational mapping, as visible stellar landmarks disappear. These migrations would likely be slow and resource-intensive, but could ensure genetic diversity, cultural exchange, and risk mitigation for species or civilizations confined to otherwise static environments. In this sense, even amid universal growing isolation, pockets of dynamic activity and adaptation may persist. Finally, reflecting on the philosophical implications, the darkness left in the star's wake invites reconsideration of human identity, purpose, and our relationship to the cosmos. The night sky with its myriad stars has been a source of wonder, guidance, and existential reflection throughout human history. In its absence, meaning may be found in new forms, through mastery of complex systems, the deepening of internal consciousness, or connection to subtle cosmic rhythms once unnoticed. The challenge of enduring in a starless universe might inspire new ethical frameworks prioritizing sustainability, intergenerational responsibility, and harmony with the subtle cosmic environment. In doing so, humanity and its successors continue the ancient tradition of finding meaning in the stars, even when they no longer shine. Thus, while the extinction of stars marks a profound transformation in the cosmic landscape, it does not signal an absolute end to complexity, life, or consciousness. Instead, it opens a new chapter of adaptation, innovation, and resilience, guided by gravity's unyielding pull, quantum phenomana's subtle whispers, and the indomitable spirit of life reaching into darkness to create light anew.